Right, so this is the second part of my kind of electrode potentials video or series, I suppose, of videos that I'm doing. This one's going to focus around the electrochemical series, which is a kind of an extension of electrode potentials. It gives them a bit of context, and it's all based around this table that I've got in the middle here, which I've stolen from a CGP textbook. But this is the electrochemical series. In reality, this obviously doesn't cover every single element, every combination of things that there could be. In an exam, you might find a bigger version of this. You probably will find a smaller version of this, and they'll include within the table the particular half reactions that they want you to use. They may give extra ones, which you do not need to use, and so it will be your responsibility to find the correct half equations when you're actually doing the work, basically, when you're working out particular questions. And at the end I'll go through a couple of questions from some past papers from the old specification. So within this table, all of the reactions given, the half reactions given, are reductions. So we can see all of them are gaining electrons, oil rig and all that. The reduction is gain of electrons. And generally speaking, it's organised from most negative at the top down to most positive at the bottom. And then obviously there's all the intermediate ones that are there. I've seen a couple of questions before where they've given very small sort of versions of this table, and they have given these in different orders. So just be aware that based on the type of question, don't assume that one at the bottom is going to be the highest value and the one at the top is going to be the lowest. You need to work out if that is exactly the case. If you do a bit of digging on the internet as well, you might find these particular values and this format referred to, or each one referred to as standard reduction potentials. It starts, I think, to get quite confusing with regard to the AQA way of working. These just electrode potentials is the way they're going to do it. They are always written as reduction equations, which I'll come on to in a bit, sort of how you best to use those. But if you start digging around on the internet, you will find some stuff that potentially makes this whole thing a little bit more confusing, and yeah, can make it just a little bit more difficult. So try not to overthink it. If you want more depth into it, by all means, go and research it and add extra stuff in. So this table, in my last video of electrode potentials, I sort of alluded to some key points in relation to sort of negativity and the positivity of the actual electrode potentials themselves, and you can see them all obviously in the table here. The more negative an electrode potential is, the more likely, to an extent, you could say the more reactive, particularly in terms of metals, you could say the more reactive that metal is. And that does stand true. We've got our magnesium here, then we've got things like copper up towards this end. So we can see that the less reactive a metal is, the more positive its value. The more reactive is, the more negative its value. And that all takes into account that when metals react, invariably they lose electrons. They are oxidized. The oil rig oxidation is lost, so they lose electrons, they are oxidized. And so the more negative a value is, the more reactive the metal is, the more likely it is to undergo oxidation, or the more easily it undergoes oxidation. Or in terms of the equilibrium, you could say the further the equilibrium is shifted, the position of equilibrium is shifted towards the left-hand side of this particular reduction that's shown. On the flip side of that, down the bottom here, our positive values are the complete opposite. They tend to be non-metals, a little bit different things like manganetes and stuff, where we got some compounds, some ionic compounds there, or some ions there, which we'll ignore for now. But if we just look at the bromine and the chlorine, our non-metals, classically when they react, they gain electrons, they are reduced. Well, the higher the value here, the more reactive they are again, the more likely they are to undergo reduction, which is kind of, hopefully, makes some sense. Now, this table, what do you need to be able to use it for? So, you need to be able to, and I'm going to pick a couple of half equations off here and sort of show you and link into things in the last video, and show you what you can actually use this table for. So let's say we had two half cells. Let's say that half cell was involved, or let's say the overall, that was a terrible tick, what I bothered for there we go. The overall electrochemical cell involved a half cell of magnesium and magnesium ions, and let's have bromine and bromide ions. I've got a cold. Ugh. So that's our two half cells here. These are the two half reactions that are going to go off. One would be in one beaker, one would be in the other beaker. Now we have two separate reactions here. We've got this, obviously, the equilibrium here, and we've got this equilibrium down here with the bromine. Now what we would find in this case is that, and this is true of any situation, the more negative electrode potential will be the one where oxidation occurs, and the more positive is where reduction will occur. So more negative, and that's a good thing to remember. More negative equals oxidation, and more positive equals reduction. In the overall electrochemical cell, you will have redox occurring, you will have reduction and oxidation occurring. It's up to you to work out where that's taking place. So in this one, we would find the magnesium ions would be oxidized, the magnesium atoms would be oxidized to magnesium ions, and we would find the bromine molecules would be reduced to bromide. So we would find that we'll write out this as an oxidation, so our magnesium would become magnesium 2 plus 2 electrons, and then down here we would find that our, just as is written there, our bromine would become bromide ions. More negative, oxidation taking place. The more positive is where the reduction is taking place. And that's really that. We could work out an EMF for this particular reaction, and we could say the EMF is, in a previous video I said it's the right hand side minus the left hand side, or it's the reduction minus the oxidation. Now we know that this is the reduction, so this would be 1.07 minus the oxidation. Well, that's minus 2.38 in this particular case, and so our EMF for this reaction would be 3.5 volts. And that's the kind of thing from an exam perspective that you need to be able to do. You need to be able to use this table, you need to be able to calculate EMFs, and I'll do a conventional representation in just a moment as well. One thing I did want to touch on is the idea of, and some people may ask this question, is that although these are shown as reductions, when we look at this in an oxidation sense, which is obviously the reverse that it's shown here, we do not reverse this sign. Now this is where I think there can be some confusion and where it can get a little bit more difficult, because certain places on the internet you will find that they do say reverse the sign, but then they also work out EMF in a different way and they add the two values together. So my advice would be stick with the way I'm doing things, and you should have no issue from an exam perspective. You will be absolutely fine and be able to answer all the questions, and I'll show you later on some proof for that. The last thing here, if I was looking at this particular electrochemical cell here involving the magnesium and the bromine, we could do a conventional representation for that. Now, as with anything else, we would do, I don't know why I scrolled down there, I didn't need to in the slightest. We would put a salt bridge in the middle, which is important. Now, our left-hand side is going to be where our oxidation reaction's taking place, and our right-hand side is going to be where our reduction takes place. Remember, that's always the case unless it's a standard hydrogen electrode, where that hydrogen part will go on the left regardless of whether it's oxidation or reduction, and I'll come on to what I mean by that in just a second. So, our most oxidized species goes on the inside here, so we've got our bromine there and our magnesium ions. On this side we're going to have a comma there, because actually if you look at this, they are both aqueous. We would probably want something like a platinum electrode as well, given that none of these are solid. We'd have to use something to catalyse that reaction to allow the actual reduction process to occur, something on which surface that can happen. That would be my conventional representation. Most oxidised species, here we've got 2 plus, here we've got 0, here we've got 0, here we've got -1. So most oxidised goes next to the salt bridge. This side is your oxidation, this side is your reduction. Stick in any platinum electrodes if you need it. Bish bash bosh. That is hopefully nice and simple. What I thought would be worth mentioning at this point is that you have to work out sometimes which reactions actually taking place. And what I mean by that is if we take the hydrogen one here, so we're looking at this one here, I'm going to get rid of these, I don't know what that symbol means. Boop. Oh no, I've rubbed the whole thing out. That's a nightmare. There we go, that'll do. So, where am I? I've lost hydrogen. So if you look at this one here, then we can see that has that 0 value, which is our arbitrary. These are all compared to that, which is the whole purpose of the standard hydrogen electrode. Now, if we had hydrogen, this occurring here, but we paired that in 1/2 cell up with magnesium here, we would find that this magnesium, so with Mg and Mg2 plus, we would find that this is where oxidation would occur because it's the more negative value, and this half we would have reduction occurring. So we would have the H plus ions gaining electrons, as is on there, going to H2, and this side we would have the oxidation, which would be the Mg to the Mg2 plus 2 electrons, which isn't particularly outstanding. However, if we had this same hydrogen here, but this time we did it with, say, the silver, we would find that hydrogen H2 with silver plus, now we would have the opposite occurring, because the hydrogen now, looking at my table at the top here, has the more negative value, the silver has the more positive. So hydrogen would now be undergoing oxidation and the silver would now be undergoing reduction. So it all depends really on the half cells that you've got as to whether oxidation or reduction will take place. And that's a very important thing to remember, and you've got to always be aware of that within the exam. So now we would find the opposite reaction happening. The hydrogen gas would be being oxidized to hydrogen ions there, balance the whole thing up, and the opposite would be true here, in that our silver ions would be reduced to silver. Just a point to be aware there. So although in one situation this is reduction, it is then oxidation depending on the other one. And the more negative is always going to be the oxidation reaction, the more positive is always going to be where the reduction takes place. We can link this same concept really to feasibility, in that when we carry out, when we work out EMF for a particular electrochemical cell, which involves the two half cells, we are always looking for a positive EMF value. If we are given certain combinations, you could be asked, will this be feasible, etc. Well, depending on what we've got present, provided that the EMF is a positive number, as this one is, you will find that would be a feasible reaction. If you work out that your EMF ends up being negative for whatever reason, that would not be feasible. And that ties slightly into things like displacement. We can look at displacement reactions in this same sort of vein, really, and we can say, actually, yeah, if we added this to this, it would work. So the example, I'll give you an example. If we added zinc metal to magnesium ions. Now the magnesium ions in that situation would end up being reduced to magnesium atoms, and the zinc metal would be oxidized. In that particular situation we had zinc and Mg2+. Now the problem is, because of the nature of these electrode potentials, there's no way that reaction could take place, because the zinc being oxidized would mean this has to be the more negative, whereas actually in reality the magnesium is the more negative value, so that could never happen as a reaction. So it goes some way in explaining things like displacement as well, and it just helps in that sense a little bit. So just be aware of feasibility and the fact that your EMF value for a feasible reaction needs to be positive, and that's an important thing. And that ties into sort of the idea of entropy and things as well. We've got a Gibbs free energy, and you can actually incorporate. You don't need to for A level, but you can actually incorporate electrode potentials into Gibbs and work out feasibility in a proper sense, if you like, with some nice fancy equations, which I think you can get on Wikipedia and on the internet and all the rest of it. But you don't need to be able to do that for A level. But obviously, if anyone wants to have a little gander at that, then you're more than free to do so. The final thing really that I want to talk about is now in relation to this table, and it's oxidizing agents and it's reducing agents. And the reason being that they quite like this in exams, and I'll show you a couple of questions at the end. They like asking questions about oxidizing and reducing agents, and really hammering the fact of where's our weakest oxidizing agent, strongest, etc., and all the rest. Now I'm going to get rid of this if I can. Oh no. Oh. Do you know what? Do one, just stay over there. Probably should have just cut that out, but I'm just going to keep going with it. So, we have our electrochemical series there. A little bit of an interlude, that was nice. Within this, we've already said we've got the negative values at the top, we've got positive values at the bottom, blah, 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 blah. Now, an oxidizing agent is obviously something that oxidizes something, and a reducing agent, these are not in relation to this table, I'm just doing these as separate just bits. So oxidizing agent is something that oxidizes something, and reducing agent is something that reduces something. Now in the process of that though, from an electron transfer perspective, an oxidizing agent is itself reduced, and a reducing agent is itself oxidized. Because in order for a reducing agent to work, so a reducing agent reduces something. Now, if that thing is reduced, then it's a gain of electrons. Well, those electrons come from the reducing agent itself, which is oxidized, and the opposite is true of the oxidizing agent. If you struggle with that idea, just sit and sort of really think about it for a moment. But it does make sense, I promise you. So an oxidizing agent is reduced, and then a reducing agent is oxidized. So let's concentrate on this first one here. So an oxidizing agent is reduced. Now, The more likely, therefore, a substance is to be reduced, the better it will be at being an oxidizing agent. So the more easily it's reduced, if you like, the better it will be at being an oxidizing agent. So if we look at our table, the one that's the half reaction that's best at being reduced would be the one that has the most positive value. So down here, this one here is going to be the one that has, or it's going to contain the species that is the best oxidizing agent, because it has the most positive value. Now, be very aware in this situation that there are two species involved in this half reaction. There's the manganate ion, MnO4-, and there's the manganese ion, Mn2+. You need to decide which of these is the correct oxidizing agent. So if you were asked from this table above, from the table here, which would be the strongest oxidizing agent? Well, you're looking for the one that's best reduced, most easily reduced, higher value. So it's going to be either one of this, manganate, or it's going to be the manganese. You've got to decide which one. Well, our oxidizing agent is reduced, so you need to pick the species that is going to be reduced. Well, it has to therefore be the MnO4-. So from this table, the best one would be the MnO4-, because it would be reduced to Mn2+, going from +7 there to +2 here in terms of oxidation states, and therefore that being reduced happily is doing, it is a good oxidizing agent. And actually, we know it's a pretty good oxidizing agent. Dichromate is again also a good oxidizing agent, but we know this from redox titrations, and we can use this to oxidize things. There's a cool thing you can do. I'm trying to think what you add. It's manganate and I think it's concentrated sulfuric acid or something. You end up making some heptoxide, but you can make this this cool thing that ultimately is super oxidizing, which just basically sets fire to things, which is quite funny. But anyway, that's just that. It's good oxidizing. So there we go. On the flip side there, our reducing agent is something that is in itself oxidized. So on the complete opposite here, we're looking for the thing at the top would be the best at being oxidized. It would be the best reducing agent up here, because it is the one that has the lowest electrode potential. Now this is the important part again. You've got to work out, if you know this is the half reaction that's going to involve the best reducing agent, you've got to decide whether it's the Mg2+ or it's the Mg. Well, our species needs to be oxidized in the process of being a good reducing agent, so we have to look for the thing that is the unoxidized version, if you like. So it would have to be magnesium, not the magnesium 2+, because in the process of being a reducing agent, the magnesium would be oxidized to magnesium 2+ ions. And that's a very important part to remember there. You've got to get that right. If you're at Mg2+ or Mn2+ there, that would be incorrect. To flip this round, you could have on this table the complete opposite. You could say which one of these is the worst oxidizing agent, which one is the worst at doing that. Well, the worst oxidizing agent would be the one that is less easily reduced. So you would go up here and you would look at the top there, and it would be within this top portion, and the opposite of the worst reducing agent, etc., etc. So it's the complete opposite of what we've got, and I'll show you that in a couple of exam questions now. I think that pretty much covers everything about electrochemical series from a theory perspective. So I think we'll have a go at putting some of those ideas down on paper now. A couple of exam questions. Alright, so this is a question from, I think it's June 2014, from the old specification, but a lot of these questions are very similar to what will be in the new ones. The new specimen papers. I will do a specimen paper run through at some point of the full A level as well. So first one here, given some standard electrode potential data in a nice little mini electrochemical series here. Our more negative is at the top and our more positive is at the bottom, which is great. So give the conventional representation of the cell that is used to measure the standard electrode potential of iron as shown in table 3. Well, there is table 3. So we know that we need to include the hydrogen electrode. So we're looking at, it's not in here, granted it's not in there, which is a bit sneaky of them, but we need the hydrogen electrode. That is on the left hand side always. Our more oxidized species goes on the next to the salt bridge, so we're going to have an H+. We're measuring the standard electrode potential of iron, so it's going to be this one here, the Fe2+ Fe. So that's going to go on the inside there. Different phase, Fe. Don't need any platinum there. What we will need here is about like that, something like that. So we've got hydrogen ions. We've got iron ions next to the salt bridge. We've got our hydrogen gas, and we've got our platinum electrode, very important. And we've obviously got our iron there. No need for a platinum electrode here because iron is solid. That would be used as the electrode itself. Okay, second question. With reference to electrons, give the meaning of the term reducing agent. So I didn't actually go through this specifically with reference to electrons in the last bit when I was talking about oxidizing agents, etc. But a reducing agent is itself oxidized. So you could say it's oxidized, but that is not in reference to electrons. So we would need to say it loses electrons, basically. 1 mark, nice and easy. Meaning the term reducing agent loses electrons. Ultimately, it reduces something by itself losing electrons. And it's important to sort of also kind of the idea being those electrons are then given up. So it loses electrons, and I suppose we could say it donates them. So it's not just the idea of it just losing them, it loses them to the thing that is being reduced, and that's the important part there. Identify the weakest reducing agent from the species in table 3. Explain how you deduced your answer. So we look at we're looking for the weakest reducing agent. So reducing agent, remember, is oxidized. A reducing agent is oxidized. So we want the one that is less easily oxidized. So we're looking at this electrode potential there, the one that is going to be less easily oxidized, or the one that's less likely to undergo oxidation. That's the more positive electrode potential. So, reducing agent, the thing is going to be oxidized, so we need to look for the unoxidized form within here. Well, I think we're going to be looking at chlorine is going to be our, yeah. So we've got 0 here in our oxidation state. Over here we've got chlorine being +1 minus 2. This is +1 here. It's a funny format of chlorine. So the unoxidized format there is going to be chlorine. And our explanation for that has the highest electrode potential. How are they writing that? E, yeah. Highest standard electrode potential there. Done. 2 easy marks. I'm going to leave the rest of this question now, and I'm going to go on to another one which has a bit more details in it. So this was the June 14 paper. Now I'm going to look at June 15, question 6 on there, as another one of showing you some different ideas. So a very similar layout again. Table 6 contains some standard electrode potential data. This time again, we've got electrochemical series in order. More positive at the top this time, more negative at the bottom. They flip that round. No issue, reason they can't do that. And we give them these not as equilibrium now, we give them as just as half equations. But we have a more positive at the top, more negative at the bottom. All nice and numerical. In terms of electrons, explain the meaning of the term oxidizing agent. Well, an oxidizing agent is itself reduced, so it gains electrons. So I suppose you could say it's an electron acceptor. That's what I think we'd be looking at, sort of the electron acceptor. Okay, identify the weakest oxidizing agent in table 6. Right, the weakest oxidizing agent is the one that's less likely to be reduced. So the less likely to be reduced is going to be the more negative value. So most negative value is going to be down here in the iron half equation there. So weakest oxidizing agent is the one that's less likely to be reduced. So it's going to be this one. Now again, the reduction would be going from the 2 plus format to 0. So the weakest oxidizing agent would be Fe2 plus. Again, just once more on that. Weakest oxidizing agent is the one that's less likely to be reduced in that whole thing. Therefore, the one that it has the lowest electrode potential, which puts us at that bottom portion here. Whether it's 2 plus or just Fe, you've got to decide, well, in the process of oxidizing agent, a substance needs to be reduced, therefore the 2 plus would become the Fe2 plus would become the Fe in that process of oxidizing, but of course it's very weak, and it has this negative value, and the reason there, explanation, lowest electrode potential. Okay, 6C. Write the conventional representation of the cell used to measure the standard electrode potential for the Ag plus Ag electrode. Okay, conventional representation. Now we can just write this out. Now we're good at this. We know it's going to be the platinum, it's going to be hydrogen, it's going to be H plus, it's going to be salt bridge, it's going to be our oxidized format from the silver there, and it's going to be silver. And there's 4 marks for this. 4 marks. That's probably going to get you 1 mark now. State the conditions necessary when measuring this value. Right, so we're going to have pressure, 100 kilopascals. And this ties into my first video actually a little bit. Temperature, we're going to have 298 Kelvin. All solutions at 1 mole per decimeter cubed. Nice there. I think actually for this question we got 2 marks for this part. I think it's 2 marks here, but you don't know It doesn't say give two conditions, it says give the conditions necessary, so I would put down all three of those. Obviously just make sure you get them correct. Don't put down pressure as 15,000. Put it in the right numbers, but I'd put those things down. Obviously, if it says give two conditions, give two, but it doesn't. It just says state the conditions necessary. So you're better in that case, I think, to put slightly more. Use the data from Table 6 to explain, in terms of redox, what happens when a soluble gold 1 compound containing Au plus ions is added to water. Ugh, I hate these questions. But so we're going to go right the way back up to our table. So we're looking for this guy here. We're looking for the Au plus, and we are adding that to water. So we're going to be adding it to this one here. Now, we've got two half equations. We've got to decide what's going to happen. So this is our more positive value. So this is going to therefore be where reduction happens, and this is going to be where oxidation happens. It does say in terms of redox, explain that. More positive value is going to undergo redox, and more negative is going to undergo, and they are both positive, bear in mind, but this is the more negative. So this is where oxidation is going to take place. Now, in terms of what we've got here, oxidation would be the H2O going that way. It would be the opposite way around here, because we've got H plus is 1 there, plus 1 in terms of the oxidation states. Oxygen is 0 there, and minus 2 in the form of H2O. Therefore, oxidation is going to be the H2O going to the O2. The reduction is going to be the A plus going to the AU. Now, what does it ask us for in terms of questions? Write an equation for the reaction that occurs. So state what you observe, right, blah, blah, blah. Write an equation for the reaction that occurs. So it would be, try and remember this now, H2O plus Au plus. Now we're going to have to make sure we get this right in terms of the electrons and the balancing here. Right, okay. We cannot just add this to this. We're going to have to multiply this one by 4 so that we have the correct number. So this is going to be 4, 4, and 4. This is going to remain the same, so it's going to be H2O plus. Actually, no, we can simplify that slightly, can't we? No, we can't. No, 2H2O plus 4Au plus, go back down here, scrolling around, 2H2O plus 4Au plus is going to go to 4Au plus, I think it was 4H plus O2. Let's go back up there, check our other bit. O2 and 4H plus, yes. So that's our equation. Okay, so, oh no, I've managed to switch this round. Oh no, got the pen the wrong way around. Apparently you can just rub things out. How does this work? Oh, no way. Anyway, so use the data to explain in terms of redox what happens when a soluble gold compound containing Au plus ions is added to water. So right, in terms of redox, what's going to happen? Well, our explanation here is going to be that the Au plus Au equals highest, that's where the reduction is taking place, the highest electrode potential. And so we could say that that is going to oxidizes H2O. I'm going to add in here actually, make it really clear what is oxidizing H2O. So this has got the highest electrode potential, this particular half equation, and the Au plus is therefore going to oxidize the H2O. Observations, what would we see? Well, we're going to produce gold. So gold metal produced would be an observation. Another observation, really easy one, would be oxygen gas produced. Observation, bubbles of O2 gas. 4 marks there, easily covered 4 marks there with the correct equation, explanation, and then observation there as well. There is only one observation needed, but whichever one, bubbles might be the easiest one to put down there, to be honest. Scrolling down, this question continues. Here it is again. Oh, they've given us the table again. That's nice of them. So a cell is made by connecting Fe2 plus Fe and Ag plus Ag. So Ag plus Ag, Fe2 plus Fe. Be careful when they give other iron species in a. Is this a new table or a different table? Oh, this is a. I know it is different. Same table? I don't know. Don't use the wrong. They've done this on purpose. Do not use the wrong electrode potential here. Just go, oh, there's iron. I'll use that one. So it's got to be this one here. Now EMF, as always, is going to be our. Basically, it's going to be where the reduction takes place, the more positive value minus the negative value. So it's going to be 0.8 minus minus 0.44, which is going to be 1.24. So I'm going to use a calculator. I'm bailing. 0.8 and 0.44. Yeah, 1.24. So 1.24. Get your units in there as well. Oh dear. Still keeps going, this question. Suggest why potassium chloride would not be suitable for use in the salt bridge of this cell. Okay, this is a suggest question, which means you've got to use your scientific brain to try and work an answer out. So it's 1 mark. If you can't get it, don't worry about it. It's a real bit thinking out there. We've got chloride ions and we've got silver ions. Silver chloride precipitate would be formed. So basically those chloride ions would react with Ag to produce AgCl precipitate, which we don't really want. It's just going to mess things up basically. We want our the ionic substance within our salt bridge. We want ideally to be completely not taking part in that reaction. It's only to allow for the ions to flow and to complete the circuit. Okay, final bit, 6F. Use data from table 6 to explain what happens when a solution of iron 2 chloride is exposed to the air. So iron 2 chloride, what we're looking at here is iron 2 plus ions. When that is exposed to the air. Now, what we've got here is 2 potentials. It's a nice little question, this. When it's exposed to air, we're going to ultimately find that we're going to have this is one part of it, which is going to occur there. And we've got this process, one of these two occurring down here. Now, you've got to pick whether it's this one or this one, but there's an easy way of working that out, and that this is the more positive value of both of those. So this is where reduction must take place, because the oxygen there is going to go from 0 to -2, which is great. So the oxygen is going to be reduced, but actually in the process the oxygen is going to do some oxidizing of its own for something here. Now it cannot oxidize the iron 2 plus ions here down to Fe, because that would be a reduction. So it must be that it's going to oxidize the Fe2 plus to Fe3 plus. So Fe2 plus is going to become Fe3 plus in the process. Scrolling down, scrolling down, scrolling down. So Fe2 plus will be oxidized to Fe3 plus, but that's a description of what will happen, because linking word explanation, because O2 electrode potential is higher, therefore reduction higher than Fe2 plus electrode potential. There we go. Therefore reduction. Yeah, perhaps we wouldn't even bother with that actually. There we go. Yeah, so Fe2 plus will be oxidized to Fe3 plus because the O2 electrode is higher than that. Therefore, reduction will take place at the oxygen portion, and the iron 2 plus therefore must undergo oxidation. Did I say reduction there? Yeah, reduction takes place at the oxygen to water, and the iron 2 plus will be oxidized to iron 3 plus. There's a couple of questions, load of stuff on electrochemical series. As always, I hope that's been of some help. Any problems, let me know in comments or get on me Twitter and that. But yeah, there you go.